So for those of you taking Chemistry 216, Inorganic Chemistry, I want to give you a little bit of a taste of what's coming at you in week one. First and foremost, review your quantum mechanics. N, L, M sub L, M sub S. If you don't know what I'm talking about, then you need to go back and reread your general chemistry textbook, specifically a chapter on quantum mechanics. I believe it's chapter 6 or 7. And get caught up, or refreshed, I should say, on that. So I want to go through Lewis dot structures for diatomic nitrogen, diatomic oxygen, and nitrogen oxide, or nitrogen monoxide. So I'm not going to go through the whole rules for octet, the octet rule, formal charge, and all that kind of stuff. You should know that. So for nitrogen, diatomic nitrogen, we have a triple bond. We have lone pairs on each nitrogen. For oxygen, we have a double bond. You have 2 lone pairs on the oxygens. And here I'm going to take the time to put this formally. So nitrogen has 5 valence electrons. Oxygen has 6. Okay? See why it's important to count these up. We have 11 electrons. Right there, an odd number of electrons should give you pause. What I like to do, just first put in a chemical bond, a single bond. Okay? So that's 2 electrons. We have 9 left over, so we can just throw them in as lone pairs and then see how that works out. So I'll just start with the nitrogen. So 2, 4, 6, 8, and 9. 1 electron is not a pair, right? So, but I'm going to call it a lone pair for now, in the sense that it occupies a region the same way a lone pair. Well, we've used all of our electrons. So now we have to figure out, is this okay? The answer, of course, is no. 2, 4, 6, 8. Nitrogen obeys the octet rule. 2, 4, 5. Well, 5 is not 8, so that's not going to work. If I do this, take some electrons, again, 2, 4, 6. That doesn't obey the octet rule. 2, 4, 6, 7. That's still not obeying the octet rule, but it's a little bit better. Well, what I'm going to do is I'm going to take a lone pair, and now I'm going to make it into a double bond. Okay? 2, 4, 6, 8. Nitrogen is obeying the octet rule. Oxygen, 2, 4, 6, 7. It's not obeying the octet rule, but for now we'll pretend that that single electron is behaving exactly like a lone pair. Now the question is, do I put that single electron, what's known as a radical, on the nitrogen or the oxygen? So I've redrawn this, where now oxygen, 2, 4, 6, 8. Oxygen obeys the octet rule. Nitrogen, 2, 4, 6, 7. It's not obeying the octet rule. So I'll put a little reverse sign. So which is correct? Okay? This is where you have to remember the concept of formal charge. So let's count up the formal charges for the nitrogen and oxygen in both of these molecules. Okay? Again, if you aren't grabbing your periodic table and starting to write down to do this calculation yourself right now, you need to go back and review chapters 6, 7, and 8, which are quantum mechanics and then into chemical bonding in the OpenStax textbook. And of course your notes. You should have notes from Chemistry 111. How do we calculate formal charge? Well, for the nitrogen, nitrogen brings in 5 valence electrons. And we want to count how many electrons it has as lone pairs and how many it's sharing in chemical bonds. So the easiest way to do that, well, 2, 4, 5, 6. we count 1/2 of each chemical bond. So again, I'll do that again. So 2, 4, because each lone pair is completely owned by the nitrogen. So 2, 4, 5, 6. So 5 minus 6 is -1. For the oxygen, its formal charge is going to be 6. It has 6 valence electrons. 6 minus 2, 3, 4, 5. So 6 minus 5 is +1. Okay? We have a formal negative charge on the nitrogen, a formal positive charge on the oxygen. Let's see if we can do better. Ideally, molecules will have 0 formal charge. However, there are circumstances where formal charge is absolutely necessary. But here we've got a choice, because we can move that radical electron, that free electron, back and forth between the nitrogen and oxygen. So now let's try this again on the second variation. Okay? So we have formal charge 5 minus 1, 2, 3, 4, 5. Well, 5 minus 5 is 0. That's a good sign. And for the oxygen, you might suspect, we're going to have 6 minus 2, 4, 5, 6. 6 minus 6, of course, is 0. Purely from a formal charge perspective, this is the correct description. You could make an argument that this could be a resonance structure, but that's really not relevant, simply because no charge is better than a charge. So this structure would not be considered to be a significant resonance structure in any shape, form, or fashion. But it's going to bring us to another problem. How can you have an octet rule based on 8, and 2, 4, 6, 7? 7 ain't 8. Okay, so this is a problem, right? And there's no way to get around it because we have 11 electrons. We have an odd number of electrons. What this is telling you right now is theory is seeming to kind of hit a brick wall. In other words, Lewis dot theory specifically. We have this molecule that exists, and we can't quite fit it into the octet rule without having to violate the octet rule. You're not doing the octet rule wrong. Okay? That's the most important thing. You are not misusing the octet rule. What this is actually telling you is that there's a fundamental problem with the octet rule. Okay? This is why you're taking Chemistry 216. We're going to see that chemical bonding is more advanced than the octet rule. Now, another thing about these two molecules, diatomic nitrogen and diatomic oxygen, is that, well, looking at these Lewis dot structures, which again would be correct from a Lewis dot structure point of view, we can predict the magnetic properties of both of these molecules. We would predict that diatomic nitrogen is diamagnetic. What does that mean? It means that it's slightly repelled by a magnetic field. And just kind of take you down a trip of memory lane, if I have hydrogen versus helium, the atoms, one electron for hydrogen, 2 electrons for helium. One unpaired electron means that this is paramagnetic. Hydrogen, and as an atom, is strongly attracted to a magnetic field. Helium has both electrons paired. That makes it diamagnetic. Okay. What would you predict for O2? Okay, I'll give you a moment to think about this. Look at the structure, the Lewis dot structure. Should this be para or diamagnetic? What about NO? Should it be para or diamagnetic? Even before drawing the structure, 11 electrons, an odd number of electrons, that by definition is going to give us a paramagnetic species, unless it dimerizes. But we're talking about the monomer. So NO is paramagnetic. Okay. And oxygen, O2, dioxygen, we predict that it's diamagnetic, but it's observed to be paramagnetic. Write that down. Okay. Now, why is that significant? Well, don't trust your lying eyes, because, again, the Lewis dot structure tells you, 2, 4, 6, 8, 10, 12. I got all my electrons in there, 12 electrons, and they're all paired together. By definition, that's diamagnetic, just like nitrogen. But what's observed, again, the real world, says, no, O2 is actually paramagnetic. How can we resolve this? Okay? Well, the answer is we cannot resolve it with Lewis structures. Okay? We are going to bring in a new chemical bonding theory called molecular orbital theory, which sounds worse than it is. And that's going to allow us to explain what's going on here. Fundamentally, Lewis dot structures treat the electron as a particle. Okay? Again, if we go back to quantum mechanics, we know from quantum mechanics that electrons have particle properties like mass and charge, but they behave like waves, wave-particle duality. What molecular orbital theory does is that it treats the electrons as waves, wave functions, and then uses that form of mathematics to create chemical bonds and the equivalent of lone pairs and so forth. Lewis dot structures are absolutely fantastic for so many different aspects of understanding chemical connectivity, and then we go from there to Vesper. But when Lewis dot structures fail, in general chemistry, we just kind of, well, it's an octet rule violation, that's fine, but that is not going to fly in Chemistry 216 and some of your upper division courses. So what we have to do is you have to bring a more advanced theory in. For those of you who have taken organic chemistry, you've actually seen molecular orbital theory. I'll put an asterisk there, molecular theory light, if you will. And you might be saying, what's he talking about? We didn't do that. Yes, you did. Aromatic molecules, the benzene ring, that's actually the first step to get you into molecular orbital theory. In general chemistry and organic chemistry, we refer to them as resonant structures. But resonant structures are also a failure of the octet rule of Lewis structures. So odd electron species, resonant structures, deficient octets, expanded octets, those are all symptoms that there's something wrong with the octet rule. And it comes down to the octet rule was created, Lewis structures were created before quantum mechanics was fully fleshed out as far as chemical bonding. So we will be investigating molecular orbital theory at the beginning of Chemistry 216. And to make your life easier, and by extension my life easier, please go back and review your notes on quantum mechanics, because everything in molecular orbital theory is based on the foundation of quantum mechanics. It's just now an extension of that. Okay? So in general chemistry, we kind of ended with Lewis dot structures from a structural, from a molecular structure point of view. Now we need to go beyond that. And this won't just be for small molecules like O2. We will eventually expand our understanding of chemical bonding into the D block elements, the transition metals, metals like iron and cobalt. So we're going to need that molecular orbital theory to do so, or variations of it. So again, I will be posting more material and sending out emails as we get closer to the beginning of the semester. Technically, I can't hit you with any homework because we haven't started yet, but day one, You need to know everything from general chemistry, especially again with quantum mechanics.